So for this last video on chapter 15, we're going to look at a similar situation what we've seen before, but we're going to be covering something called cycloaddition reactions. In particular, this reaction called the Diels-Alder cycloaddition, or a 4+2 cycloaddition. And so all that's happening here is we're having two different alkenes essentially reacting together to form this cycloalkene using heat. And the name 4+2 cycloaddition comes from the number of electrons, or pi electrons, involved in the transformation. So we have, on the left here, we have a molecule with 4 electrons, right, 4 pi electrons, right, those two double bonds, and then a molecule with 2 pi electrons. And so we refer to these as, and we're going to see the same system, right, this is the same general setup as every single Diels-Alder reaction we'll see, in that we have a diene, right, two alkenes, a diene, and a dienophile, right, meaning, right, a diene lover. So these two pieces come together to form our product here, right, our Diels-Alder product. And we're always going to see the situation where we have 3 pi bonds, right, these 3 double bonds, and the transformation that we end up with is 2 sigma bonds, right, 2 new covalent bonds and 1 pi bond, as we can see here, right? We have 3 total pi bonds that have become 2 sigma bonds and a pi bond. So what exactly is happening here? So, not unsimilar to what we've seen already with the pericyclic reactions, we have our diene and our dienophile, and when they react together, we form these new covalent bonds connecting the 2 pieces together, and we shift around that last double bond, right, to kind of fill in that space here, and we end up with our cycloalkene. And these 2 new bonds that have taken place, I'll draw in blue here, or highlight in blue. Right, these are the 2 new sigma bonds that have formed, right? And our pi bond has shifted around here. Okay, and so what we're going to see here as we move forward is we can attach more things to these alkenes and dienes. And so when we encounter that, we have to remember is that this reaction is stereospecific. And we'll get into what that means. And also, right, the rate of reaction, right, how fast or slow it goes, depends on substituents, right, or on the functional groups that are on our molecules, okay? So for example, right, if we had, instead of just plain old diene and ethene, we had a situation like this, where right now we have these methyl groups here, we have our diene, our dienophile, and we're always going to be using heat, we're not going to be worried about light in any of these scenarios. But now we see we have the methyl groups on the same face, right? And this is slow. We can increase the rate of reaction by doing this combination of electron donating groups and electron withdrawing groups, right, using these nitriles here on our dienophile. And these methyl groups on our alkene are electron donating. So what we end up with at the end is a faster reaction with all these groups on the same face, right, all on wedges or dashes, depending on how you drew it. Okay, so let's take a look at why this is. And so if we look at our molecular orbitals here, something we want to consider, and we won't be going into the same level of detail as we did with the pericyclic reactions, but I've gone ahead and drawn in these MOs here for us, right, because we've kind of covered this in ad nauseum already, right? So on our diene, right, we have those 4 molecular orbitals, right, we have our, right, again, 4 electrons, and for our dienophile, we have our 2 electrons, right? And so filling those in, we see the following here. And what happens, right, when we mix these orbitals, right, when we mix these to get to our product, right, our cycloalkene, we're going to be mixing the HOMO of our diene and the LUMO, the lowest unoccupied molecular orbital of our dienophile. This is how these reactions are going to come together. And so when we do that, these orbitals are going to mix, right? Our HOMO and our LUMO, these orbitals are going to mix to get to our new product, right? Or our new molecular orbitals. Right? And overall, this reaction that takes place is lower in energy, right? This new bond we're forming lowers the overall energy of the system because we're mixing this LUMO with this HOMO. We have to make sure the corresponding new orbitals here, right, these two, are displaced appropriately. Okay, so this is the basis of the reaction, that we're just getting a lower energy new bond. And so we'll see examples of why this matters, okay, and why adding on electron donating versus electron withdrawing groups is important. So, right now we have three different situations here. I'll kind of cut these up so we can see what we're doing here. Right, notice the energy, right, we have our zero energy point, right? Let's say it's here, right, kind of in between all these orbitals. Notice, right, the energy levels are not identical for the dienophile, right, across these three different systems, right, called 1, 2, and 3. Okay, and when we fill in our electrons here for each of these systems, right, we know we have 4 electrons on our diene and 2 in our dienophile. We can see that depending on what groups we've added, it changes, right, the energy levels. And so for our first one here, right, it's the same as what we had already covered, right? We have our LUMO mixing, it's the terminology we're using, right, with our HOMO to get to our new bond here. And for 2, notice, right, we have these methyl groups, right? These methyl groups are electron donating groups, okay? And what they've done, right, is they've raised the energy of our HOMO, right? See that? It's higher in energy than number 1. And what that means is, right, it reacts faster, right? Because it's higher in energy, right? It's closer in energy to our LUMO for our dienophile. The overall energy actually gets lowered when we mix our orbitals together. Okay? And this is even more true when we have our number 3 reaction, where again we have our electron donating groups, right? Our methyl groups here. They're a little bit more electronegative than hydrogen, so they're donating some electrons into our system. And in our dienophile, notice our energy has dramatically lowered now, right? With these nitrile groups, these are electron withdrawing groups, right? Electron withdrawing groups. And these lower the energy. And notice now, right, the LUMO and the HOMO are much closer, right, than they have been before. So this really dramatically decreases the energy of the new bond formed, which is really, really favorable. And so the main takeaway here, in short, is just that the closer in energy, the HOMO and LUMO are, the more stable the product is. Right, and so we want to raise the energy of the diene and lower the energy of the dienophile, right? So we want electron donating groups on our diene and electron withdrawing groups on our dienophile, because it brings the energy of the HOMO and LUMO closer together, making for a more stable product, okay? And so when we're talking about electron donating groups and electron withdrawing groups, What do we mean by this? And so for our diene, right, we're talking about these, again, electron donating groups, right, electron donating groups. We want groups that donate electrons, right, that are electronegative in essence. And so to do that, right, for our groups here, meaning, anything bonded to that carbon, we want it to be electron donating, right? And so to make this reaction go faster, we want something that's more donating. And so this would be anything with, say, an oxygen with an alkyl group, right? This would be a great electron donating group. Methyl groups, like we've seen, also donate, and then hydrogens don't do any sort of donating, so it's slower. Okay, and for the dienophile, we want electron withdrawing groups. And the more electron withdrawing it is, the faster the reaction will go. And so we can have things like cyano groups, for instance, right, they're withdrawing electrons. Halogens also work here, bromine, iodine, chlorine, fluorine, of course. Aldehydes, like anything with these carbonyls. And then hydrogens being the slowest. Right, more electron withdrawing, less electron withdrawing. Okay? So dienophiles have the electron withdrawing groups, and dienes have the electron donating groups. So now let's take a look at the last part here in thinking about the stereochemistry of the reactions. Okay? And so the stereochemistry of our starting material remains, following something called the out-endo-cis rule. And we'll break down what this means in a second here. Out refers to the diene, endo is the transition state, and cis is the dienophile. Okay, and the sort of application is less less complicated than this maybe looks right now. So when we look at the endo transition state, what this means is, right, it's sort of this in-between state of starting materials and products. It is the favorable approach of dienophile, which is underneath our diene. So dienophile is going to be kind of coming underneath our diene here. So when that happens, it's going to look like this. So we have our diene plus, here we have a dienophile, right, with our electron withdrawing groups on it. And so out-endo-cis, right? Out, referring to our diene, are these groups here, right? These methyl groups are out, and our hydrogens are in. Okay? And on our dienophile, the cyano groups, right, are cis here to the out groups. Okay? Meaning they're going to be on the same face in a product. So we have our reaction arrow, we're drawing in our cyclohexane, right? We're always going to be seeing this take place here. And so we have our methyl groups on wedges, which will always be the case on these out groups. And our cyano groups are also on wedges. Right, we're not drawing them in, but we can, right? Our hydrogens are going to be on the dashes here. Right, these in groups. Okay. So this is the general formula here, right? These out groups on our diene are going to be on wedges, and the groups right facing away on the dienophile are also going to be on wedges. So for another quick example here, I'm going to move this over a little bit. Let's look at a similar system. So we have our diene, but let's make it already in a ring. And we have our methyl groups here, and we have our dienophile. Let's just do one thing here, so let's make this, say, a bromine, okay? And we have to remember, right, what groups are out. And so our methyl groups here, right, are pointing out still, and this bridge head, right, this CH2 in the middle is pointing right in. And so what does our product look like? Again, we want to start simplest by drawing in this ring here, okay, with our alkene there, and our out groups, right, our methyl groups are going to be on wedges, and our bromine here will also be on a wedge, and that right CH2 bridgehead, right, this in portion here is now of course on our dash, so we kind of show it like this sort of ring down below. Okay. In truth, we can flip this molecule upside down as well and get the same answer, right? Flip this is totally on its side and have the wedges all dashed and the dashed ring in here in the middle on top, but it's the same answer. Okay, but we're going to be consistent, right, just to kind of make things simpler for ourselves as we're learning these Diels-Alder reactions, and that, right, the out groups are going to be on wedges, and right, this rightmost side, right, the group kind of facing away as these two parts come together, are also going to be on wedges. So we're going to follow the same sort of setup and formula, okay, as we do more of these reactions in class.